Good evening, sir. Good evening, classmates. Today I will be presenting my article critique entitled Potentials and Impacts of Selected Negative Emission Technologies in Light of Green Process Engineering. And the goal of this paper is to evaluate and summarize the features of selected nets from various references. I also related some of the features of the nets with green engineering principles. Just to share some of the references which I used for this paper and presentation. So I have six major references, and I would like to acknowledge the author Pete Smith, and he actually appears in three out of the six reference that I used. Just to give you a background for this paper and presentation, we all know that nations have agreed to keep the global temperature well below 2 degrees during the Paris Agreement. And the initial plans were decarbonization of different sectors. So decarbonization is actually removing the dependency on fossil fuels. An example, an example is turning to renewable energy. However, climate models by IPCC have shown that in addition to decarbonization, negative emission technologies or nets are also required to achieve the goal set in the Paris Agreement. Reviewing the definition of green process engineering, it emphasizes sustainable and economic technological process designs that have minimum impact on the environment and human health. And nets are actually inherently green process engineering technologies simply because of their goal of removing CO2 from the atmosphere. However, as with any other technology, the large scale implementation of nets both have positive and negative impacts. Therefore, it's important to consider green process engineering for sustainability and protection of human welfare. So far, only a few studies have presented a summary and evaluation of nets in light of green engineering, and thus this paper aims to summarize the various features of selected nets and to identify the green engineering principles supported or impacted by each net. Let's review what are nets or negative emission technologies. Well, nets sequester carbon from the atmosphere and stores it in a different environmental compartment, such as in the soil or underground. And the result is the atmospheric concentration of carbon dioxide is lower than before the implementation of nets. And here are the selected nets that I included in this paper or presentation. Afforestation, reforestation or AR, wetland restoration, soil carbon sequestration or SES, biochar, enhanced weathering or EW, bioenergy with carbon capture and storage or BECCS, and direct air capture or DAC. A growing number of studies are establishing the different features of these nets. And these studies show that each net has a different greenhouse gas removal capacity, technological readiness, and environmental impacts. Let's briefly discuss what each specific net is all about. First is in afforestation and reforestation. Uh, Here we plant additional trees to expand the forest area and thus maximizing the carbon sink. Next, we have wetland restoration, wherein peatlands, tidal salt marshes, and mangrove swamps are restored to support the anaerobic storage of dead organic matter. Next, we have soil carbon sequestration, and it takes advantage of the no-till agriculture and other land management options to enhance the capacity of soil as a carbon sink. Next, we have biochar. This is actually my topic in the first article which I presented, and it improves the soil quality as well as sequestering carbon dioxide from the atmosphere and storing it into the soil. Next, we have enhanced weathering. So here, the carbonate and silicate weathering activities of rocks are fast-tracked by the addition of silicate materials to the soil. Next, we have BECCS or bioenergy with carbon capture and storage. It uses renewable biomass which captures carbon dioxide during photosynthesis. But instead of releasing the exhaust carbon dioxide into the atmosphere during energy conversion, it's captured and stored, resulting into negative emissions. Lastly, we have direct air capture. So in this net, we have absorption of CO2 directly from the atmosphere, either by using amines or sodium hydroxide scrubbing systems. Next, we move on to greenhouse gas removal or GGR capacity. It's actually the rate of CO2 or C or carbon removed from the atmosphere, and it's usually evaluated annually. According to McLaren and colleagues, the projected GGR requirement to achieve the Paris Agreement targets is up to 24 gigaton carbon dioxide per year for over 50 years, starting from 2050 to 2100. And that's a big number. Here we have a table summarizing the potential GGR capacities of the nets. And we can see here that BECCS and DAC have the highest GGR capacity, up to 10 gigaton carbon dioxide per year, followed by afforestation, which has up to 7 gigaton carbon dioxide per year. And the rest of the nets range from zero point 0.5 to 4 gigaton carbon dioxide per year. Moving on to the next feature of nets, we have technical readiness. But before that, what is technical readiness or TRL? From the name itself, it assesses the readiness of any technology for implementation. And this table presents the 9 levels of TRL from level 1, which is where basic principles are observed and reported, to level 9, wherein actual system proven in deployment. And as we move higher and higher to the next TRL level, it means that the technology is more and more ready for implementation. So how do nets fare in TRL? We have the highest TRL or technical readiness level for afforestation and SES at 7. And the rest of the nets, wetland, biochar, BECCS, and DAC follow at 6. But for some of the nets, the uncertainty is higher, meaning the range of the TRL is higher. Studies suggest that research and development or in research and innovation may improve the TRL, especially for DAC. Moving on to the next feature of nets, which are its potential positive impacts. And it's listed down in this table from literature. First is afforestation and reforestation. Well, of course, all of the nets have a positive impact of carbon sequestration. For afforestation, it also produces food, fuel, and fiber from the trees. And we have regulation of water and air quality. It provides habitat for biodiversity. We know that from the forests. And it also promotes job creation and recreation. For wetland storage, it promotes climate mitigation, it prevents flood, and it removes sediments and pollutants from water and air. We know that from the mangroves, that's a feature of mangroves. It provides habitat for biodiversity and promotes commercial fish and shrimp production as well as recreation. Next is soil carbon sequestration. So these are the agricultural changing agricultural practices. So we have biomass production for both agriculture and forestry. We have storing, filtering, and transforming nutrients. So that's a positive impact of SES. Improves biodiversity pool, physical and cultural environment for humans since we are changing practices here. So it promotes that. And it's also a source of raw material and carbon pool. Next, we have biochar. So this is actually the topic of my first presentation. And I already actually discussed this before, but let's review. It promotes recycling of biomass waste if we use biomass residues as our feedstock. It reduces the emissions from traditional residue burning. So in the Philippines, we have burning of rice straw, and if we turn it to biochar instead, then we are reducing the emissions from that. We have energy cogeneration because biochar is actually from combustion of biomass. It has high recalcitrance, meaning the biochar is more or less stable for a long time. It absorbs and releases nutrients. It reduces emissions of uh, other greenhouse gases and remediates soil contamination by filtering water pollutants, improves soil structure, and increases the resilience of agro ecosystem. So it has so many positive impacts. Next, we have enhanced weathering. Well, for enhanced weathering, it's the same positive impacts as with soil carbon sequestration. So I'll not discuss it anymore. But basically, the advantage is that, you know, enhanced weathering because it improves ocean acidity, then it also supports protection of the natural habitat. And we have BECCS. So obviously, BECCS is for bioenergy, it provides energy and also carbon sequestration. For that, the benefit is carbon sequestration. Moving on to the negative features or negative impacts of nets, mainly negative environmental impacts. This table shows the impacts of nets on land use, water use, energy input, nitrogen, and phosphorus, except for wetland restoration, which have no data. So first, the land use. As we can see here, SES has the highest land use followed by enhanced weathering. Nevertheless, SES and enhanced weathering can be used for other purposes as well. For example, we can still plant agriculture or forest in the land that uses SES and enhanced weathering. And on the other hand, DAC or direct air capture has a very low land use intensity, almost insignificant compared to the other nets. As for water use, obviously, nets that rely on biomass would require water, so that is afforestation and BECCS. We also have water requirements from enhanced weathering and DAC. For biochar, although it's a biomass reliant nets, it was not accounted here, probably because it was already accounted in the bioenergy part of biochar. Next, we have energy input. The highest energy input is from enhanced weathering and direct air capture. For enhanced weathering, the reason is because we need to grind the rocks that we will put in the soil. So the requirement is a very, very fine grinding of rocks. On the other hand, for DAC, right now, the process of capturing and storing carbon is still energy intensive. However, the researches are ongoing to improve that. On the other hand, we have biochar and BECCS, which have negative energy input. So that means that they generate energy instead of consume it, which is a desirable characteristic of these nets. Actually, BECCS and DAC can be implemented together. They can complement each other. The energy from BECCS can be used by DAC, while the technology of carbon capture and storage can be used by BECCS. Lastly, we have the nutrients, nitrogen and phosphorus. Obviously, biomass that, nets that rely on biomass would require nutrients such as in SES, biochar, and BECCS, and also afforestation. But the problem with nutrients is that if it washes over to bodies of water, then it will cause eutrophication. That's why we don't want to get phosphorus from the environment, too much phosphorus from the environment, and also too much nitrogen from the atmosphere. Next, we have the limitations of nets when implemented in a large scale. For AR, wetland restoration, and SES, land availability is a limitation. They can compete with land for agriculture, which means they compete for land for food. And also for AR, afforestation, climate is a limitation. For example, we cannot plant or we cannot uh, make forests in deserts or in very cold places. And water availability is also a limitation. It can also compete with water for irrigation. For wetland restoration, climate is also a limitation. Not all geographic locations can support wetland restoration or cannot support this net. And for these three, AR, wetland restoration, and SES, we have this problem called sink saturation. So that's the state wherein the rate of the nets reaches its saturation state. For example, in afforestation, the rate of decomposition of trees is just equal to the rate of carbon dioxide taken by the trees from the atmosphere. And for this tree, they say, or studies show that it's around 20 years. So the lifespan of these nets is actually just 20 years. So that's very short. For biomass, the limitation is, of course, sustainable biomass supply, but it will be an advantage if we use biomass residues. And also a limitation is suitable soils for storage. Biochar also has sink saturation, but because it's a recalcitrant, meaning it's more stable than the other nets, the sink saturation uh, comes after 100 years, according to studies. Next, we have enhanced weathering. The limitations are finite solubility of salicylic acid, availability of suitable land to apply our rocks, and energy supply, because the grinding process is an energy intensive process. We have limitations of BECCS, storage, and storage of the carbon dioxide. So that's a limitation. And also, just like in biochar, sustainable supply of biomass is a limitation. Suitable facilities. Although we can use existing power plants, we can co-fire biomass with coal. For DAC, the energy supply is a limitation. As mentioned, it's still an energy intensive process. And also the storage capacity or storage of carbon dioxide, that would be a limitation. Actually, where do they store the carbon dioxide? The best candidates for that are the empty uh, petroleum mines. So that's underground. After extracting the oil, after exhausting the oil from the ground, they can store the CO2 there. In the next section, I try to relate the different positive and negative impacts of nets to the green engineering principles. Because, as mentioned, as with any other technology, when implementing nets on a large scale, it's important to consider the green process engineering for principles for sustainability. To recap, these are the green engineering principles, and we actually have two versions. We have the 9 principles and the 12 principles. For the purposes of this report, I labeled the 9 principles from N1 to N9 and the 12 principles from T1 to T12. Here is my personal assessment of each nets on how they support or impact the green engineering principles. And let's discuss this one by one. The first principle is N2, or conserve and improve natural ecosystems while protecting human health and well-being. And most nets actually support this principle. So these are AR, wetland restoration, SES, biochar, and enhanced weathering. So how? AR produces food, fuel, and fiber, and also provides habitat for biodiversity through its forest. So it supports this principle. In the same way, in wetland restoration, it provides fish and shrimp while sheltering biodiversity. So it also supports this principle. SES can improve soil quality and thus improving soil biodiversity, the microorganisms in the soil. Like SES, biochar improves soil quality and soil biodiversity, so it also supports this principle. Enhanced weathering improves ocean acidity, as mentioned, thus protecting the natural ecosystem in the ocean, and it can also improve soil quality. Next is N5, or minimize depletion of natural resources. Nets mostly impact this principle. Since all of the nets except for DAC require very high values of land, or very high areas of land and water, and take in nutrients from the environment, they impact this principle. However, I put an asterisk here for AR and wetland restoration because although these two nets require land and water and nutrients, they also give back to the natural resources because AR produces, the forest of AR is a natural resource, and the mangroves in wetlands are natural resources. So, uh, they take, but they also give back. That's why I put an asterisk here. Next is N6, or strive to prevent waste. These two nets, biochar and BECCS, mostly support this if we use agricultural residues as biomass feedstock. Next, we have N8, or create engineering solutions beyond current or dominant technologies, improve, innovate, and invent technologies to achieve sustainability. So BECCS and DAC are now the focus of research and innovation. That's why I feel that they support this principle. Next is T2, or prevention instead of treatment. It is better to prevent waste than to treat or clean up waste after it's formed. So nets impact this principle. Why? Uh, Nets are actually a treatment to the greenhouse gas emissions problem. And so what's the prevention? Decarbonization of sectors is actually the prevention, meaning if we turn to renewable energy, that's the prevention. But nets is nets are the treatment. And some studies say that promoting nets will also promote the use of fossil fuels, because companies will just say, or can just say that, well, nets are here to treat our greenhouse gas emissions. And also there might be a misprioritization between implementing nets and decarbonizing sectors because nets are available. However, studies show that both decarbonization of sectors and nets implementation are required to achieve the Paris Agreement goals. And notice that I excluded BECCS and biochar from the list of nets here because they are exempted from impacting this principle. Why? Because BECCS and biochar are actually renewable energy sources, and they are carbon neutral. Hence, they support or they prevent CO2 emissions. Next, we have T7, durability rather than immortality. Target durability, not immortality, should be a design goal. Nets either support or impact this principle. How? On the left, we have enhanced weathering, BECCS, and DAC. And these are relatively stable technologies in storing CO2 compared to the other nets. Uh, we have AR, wetland restoration, SCS, and biochar. As mentioned, these nets on the right have um, the sink saturation state, so that they're not durable, especially the first three, which only has 20 years lifespan. Biochar relatively has a longer lifespan of 100 years. That's why these nets impact this principle. And lastly, we have T12, renewable rather than depleting. Material and energy input should be renewable rather than depleting. So these nets support this principle because AR, wetland restoration, biochar, and BECCS are all rely on biomass, which is a renewable resource. So they support this principle. That concludes my presentation. And to give my conclusions, first is despite the decarbonization efforts, nets are necessary to achieve the Paris Agreement goals. And as with any other technology, the implementation of nets on a large scale should consider green engineering principles. This report summarized and evaluated the different nets according to their potential capacities, technological readiness, benefits, limitations, and the corresponding support or impact of each net on the green engineering principles. And it was found that the different features of nets either supports or impacts the green engineering principles. Thus, it is recommended to integrate the principles during the detailed planning, LCA, and implementation of nets. That ends my presentation. I'm now ready to answer your questions. Thank you very much.